start again. Now we're going to talk about diagonalization. It's our second topic. So in general, matrix computation is hard, right? Like whether it's like squaring stuff, inverses, determinants, like they're hard things to do, right? They're not finding eigenvalues, like they're just not easy, right? And we've done a bunch of things, right, that have been like, you know, we're like, okay, well, we can do this for small matrices, like if it was like 2 by 2 or 3 by 3, maybe 4 by 4. But like, if you go to the machine learning world, you have like thousands by thousands matrices, right? There is no way in hell that you are going to compute a matrix determinant or something of that thing, right? That's a monster. So like, you know, that's, in the real world, matrices aren't 2 by 2, 3 by 3. A lot of them are very big. So what do we do if we want to compute some of these? We use something called similarity. So we say that two matrices are similar. Say I have a matrix A and B. We say that those two matrices are similar if I can say that A equals P inverse times B times P, where P is just any matrix. So if I can find some matrix P, so that if I multiply by P inverse on the left and P on the right, that they're equal, that means that A and B are similar. And we usually write A is similar to B, like that. So why do we care about this? Because this seems kind of particular, right? But what's nice about this is that if you can show that A and B are similar, that means that A and B have similar qualities. They have the same qualities. So as an example, if two matrices are similar, they have the same determinant. They have the same invertibility, right? So if one's invertible, the other's invertible. They have the same rank, the same nullity, the same trace, characteristic polynomial, eigenvalues, right? Like, so all these characteristics are the same. Right? All these like values, all these things are the same between the two. And there's more that I didn't say, but I think you sort of see what I'm getting at, is that if we have a really hard matrix A that's very difficult for us to do work with, maybe we can convert it into a much easier matrix B and do the work there. Find the determinant of B, then the determinant is the same, right? So we know the determinant of A without having to do all the crazy work. Does that make sense? Okay. So what's the simplest matrix we can think of, or type of matrix? Any suggestions?
Lower, upper, or diagonal?
Of the three, what's the simplest?
Diagonal.
Yep, diagonal matrices. So diagonal matrix is the simplest. So why don't we try and see if we can find a matrix that's similar, or find a diagonal matrix that's similar to a matrix we wanted to work with, right? Because if we have a diagonal matrix, to find the determinant, we just multiply along the diagonal, right? It's already pretty much in row-reduced echelon form, right? What else? Like trace, you just add the numbers along the diagonal, although that's the same for all of them. Eigenvalues, the eigenvalues of a diagonal matrix are just the numbers along the diagonal. You just literally read them off, right? Like it just makes stuff easier, right? So why don't we try and find a matrix D such that we can do this, where D is diagonal. So A is similar to D. If we can do that, then that means that we call the matrix A diagonalizable, because we can find a diagonal matrix. The criteria for us to be able to do that is, it's actually rather simple. It's that the eigenvectors for A have to be linearly independent. Anyone know why they have to be? Actually, sorry, I haven't gotten far enough. You wouldn't know why. Sorry. Just take my word for it for now, and I'll explain in a bit. But in order for a matrix to be diagonalizable, your eigenvalues, your eigenvectors have to be linearly independent. If they're dependent, then it's not diagonalizable. Sometimes you'll hear that referred to as degenerate. Degenerate just means not diagonalizable. Okay, so from there, how do we figure out what those P and D matrices are? Well, it's actually really easy. Once you have the eigenvalues and eigenvectors, so first step, find the eigenvalues and eigenvectors. Second step, make sure that they're linearly independent, right? So check that they're linearly independent. In this case, it's kind of clear that they're linearly independent. But then, to write out your diagonal matrix, all you do is put your eigenvalues along the diagonal and put zeros everywhere else. That's it. So in this case that we did over here, the diagonal matrix would be -1, -2, 0, 0. Order doesn't really matter as long as you're consistent. Okay? For the P matrix, all you do is write your eigenvectors as the columns of the matrix. That's it. So P in this case is +1, -1, +1, -2. And like I said, keep it consistent. So corresponding to -1, I got the eigenvalue, or eigenvector, sorry, 1, -1. Corresponding to -2, I got 1, -2, right? And that's it. You've diagonalized your matrix. So you can, maybe looking at, this matrix that we got here is a bit easier, but you can look at this matrix and you have the eigenvalues right there. You have the determinant, right? That's super easy to do. If this was like a 4x4, that'd be a lot easier, right? Or 5x5 or whatever. Does that make sense? How we did that? Cool. One last thing. So say that I wanted to figure out what a to the power of 5 is in this case for this, this matrix A. I wanted to figure out what a to the 5 is. I could do this one of two ways. The way that you guys probably already know is take this matrix, do matrix multiplication of it with itself, and then do another one with itself, and do another one, right, 5 times. That's brutal, right? I don't want to do that. You don't want to do that. That sucks. An alternative, I can go and figure out first off what d to the 5 is. We've diagonalized it. And a diagonal matrix to any power is super easy to do. You just raise each of the diagonal entries to that power. So -1 to the power of 5 is -1, sorry, and -2 to the power of 5 is -32. Okay, thank you. So there's your d to the 5. And now all you have to do is multiply it by P inverse and multiply it by P. Like that, right? So do like P d to the 5, sorry, P inverse d to the 5 P. And that'll give you a to the 5. The reason why that works out is that if you wrote out, I'm gonna do this for like a little smaller, I'm gonna do a to the 3. You would get P inverse d P, then P inverse d P, and then P inverse d P. So you get it 3 times, right? So this is like A times A times A. P inverse times P, those two cancel out. This P inverse times P cancels out. So all you get left with is P inverse on the outside, D times D times D, so D to the 3, and then P on the outside. That's it. And that always works. So for any power, all you have to do is figure out what the diagonal is by just raising the diagonals to that power, and then multiply by P inverse and by P. So 2 multiplications. Maybe you're thinking 2 is still a lot. It is still a lot. But what if I wanted you to find a to the power of 100, right? Instead of doing 99 matrix multiplications to find a to the power of 100, you can just do 2. So you always just have to do 2, right? That makes it so much easier. Does that make sense?